In this video, I will be working through all of the solutions to the VSEPR practice assignment which was posted to Google Classroom. Both parts will be contained within this video, so on Monday you're expected to complete part 1, which is questions 1 through 5, and then on Tuesday you're expected to complete part 2, which is questions 6 through 10. So if you're having difficulty with any of these solutions, feel free to skip ahead to whatever part of the video you need to in order to get those solutions. On the right side here, you can see that I have the molecular geometry VSEPR sheet that I passed out in class. There's also a copy of this posted to the Google Classroom in PDF format in case you lost yours. You're going to need this paper in order to complete this assignment. Just a quick reminder of how to use this. This far left column is your total number of electron groups. That is equal to your number of bonding directions and your number of lone pairs added together. Here you have your bonding directions. Remember, a double bond or a triple bond still counts as a single direction. We have our lone pairs here, and when you have all of that information, you can figure out the bond angle, the electron pair geometry, which I sometimes refer to as the family name, and then the geometry name, which is also known as the molecular geometry. For our first problem, we are trying to draw out BRF3, and notice BRF5, and notice that there is a star here. That means that this is an exception to the octet rule. So your central atom is going to have either too many or not enough electrons around it, but that's okay. We're going to start off with a bromine, which has 7 valence electrons because it's in group 17 or 7A. I have 5 fluorines that are trying to attach to this. So I'm going to take a fluorine, 1, 2, 3, 4, 5, 6, 7. I'm going to link it. Take another one on this side. So that's 2. 3. 4. And 5. Now I know it looks really cramped here on the screen, but remember this is going to space out within 3 dimensions. So what we're going to have here is 5 atoms bonding to our bromine, and then a single lone pair of electrons, which is going to impact the shape. Since I have the 5 single bonds and then the 1 lone pair, that's going to be a total of 6 electron groups. There were 5 bonding directions and then the 1 lone pair. So now what you would do is you go to your reference sheet, you're into the row of 6, and that means that you're going to have an octahedral geometry name. Octahedrals have bond angles of 90 degrees. And then for the molecular geometry, I'm going to look at the 5 and 1 row. So that's going to be square pyramidal. And now I have to determine whether or not this is a polar or nonpolar molecule. In your lab, you also had a column for polar or nonpolar bonds. I don't have that here. So all of these are going to be polar bonds because remember, for a polar bond, let's go in the other direction. For a nonpolar bond, there's only 2 possibilities for when that would happen. It could be a diatomic element, so 2 of literally the same atom, because these would have the same pull on the electrons, they would be right in the middle, or carbon to hydrogen. Since their desire for electrons is so similar, the electrons are going to be right in the middle. But if it's not one of those 2 combinations, like here, bromine and fluorine, you're going to have a polar bond. In order to determine if it is a polar molecule or not, you have to look at the symmetry. Now, you could use that PhET simulation in order to build it within 3D space and kind of spin it around, or you can try to look at one of these pictures from down below and then see if you have symmetry from there. So looking at my VSEPR geometry sheet that I gave you, if you go across the 5 and 1, this is the picture that you would copy and paste up here. Now looking at this picture, since there is the same atom on each of these 4 sides, this part around the center is going to be symmetrical. But this bond is not going to cancel out with the lone pair that's down below. So that means since this is not symmetrical, it's going to be polar. Alright, for our second compound, we have PCl3. This is not an exception to the octet rule, so our central atom should have 8 electrons around it when we're done. We're going to start off with a phosphorus, which has 5 valence electrons around it. I have a chlorine, which has 7, so it's going to connect right here. And I have 2 more chlorines that are going to connect. Alright, so that's my molecule. There are 3 bonding directions. There's 1 lone pair, so that's a total of 4 electron groups. So I look at my sheet, I go to the family of 4. That means that it's going to be a tetrahedral for the electron geometry. And then for the molecular geometry, because it's 3 in 1, that's going to be trigonal pyramidal. For the bond angle for this one is going to be 109.5 degrees. Now, in actuality, it's actually a little bit less than the 109.5 degrees because of this lone pair that's present. It's going to push down these bonds more than an additional bond would, but writing in 109.5 degrees is perfectly fine. All right, now for the 3D sketch. I should have 3 bonds and a lone pair according to my chart, so it's going to be this one right here. So this is what you would copy and paste into that box. And now if you look at this in terms of the polarity, this lone pair doesn't have the same pull that each of these 3 atoms would. So that means this is not symmetrical, and it would be a polar molecule. All right, for our next example, we have boron and then a fluorine and 2 chlorines bonding around it, and this is an exception to the octet rule. So I'm going to have either not enough electrons or too many on the central atom. My boron is going to start off with 3 valence electrons around it. One of those is going to go into the fluorine, which is bonding, and the other 2 are going to attach themselves to the chlorines. So in this instance, I'm breaking the octet rule because I only have 6 valence electrons around the boron. All right, for my bonding directions, it's going to be 3. There are 0 lone pairs on my central atom, so that's a total of 3 electron groups. So I go into the row of 3. That means it is the trigonal planar family. And because it's 3 and 0, that means the molecular geometry is also trigonal planar, with a bond angle of 120 degrees. For my 3D sketch, I should have 3 atoms that are spaced out and they do not have any lone pairs around them. So that would be this one right here. So this would get copied and pasted into that box. And now for the polarity. Now, geometrically speaking, this is completely symmetrical. These are all pointing in completely opposing directions. But if you consider what's actually on each of these sides, and I'll redraw this up here, one of these would be a fluorine, and then 2 of them would be chlorines. So because these atoms do not have the same pull, it might be symmetrical if you cut it through this bond, but it wouldn't be symmetrical through either of the others because the fluorine and the chlorine would not cancel out. So that makes this a polar molecule. All right, for our next example, we have SF4. This is going to be another exception to the octet rule. Sulfur has a total of 6 electrons around it. It's an oxygens family, so group 16 or 6A. I have 4 fluorines that are going to attach. So I'm going to link 1 on each of the sides of the sulfur, since I have the space to do so. Then notice here how I have these 2 lone electrons, but currently they're separated. I'm just going to redraw this to make it a little bit neater. So I have my 4 bonds going to those fluorines. And then I would also have a lone pair on the sulfur. So I usually draw those together within the final product. That way we don't miss it when we're trying to fill in our table. All right, so based on that, we have a total of 4 bonding directions. There is a lone pair this time, so that's a total of 5 electron groups. So then I look at my sheet, I go to the row of 5. This is going to be a trigonal bi-pyramidal shape. And notice that for this one, there are 2 bond angles. There's a 120 and there's a 90. That's because there are actually 2 different bond angles within the shape. So this would be the head of the family. For this one, it's not our actual picture that we're going to select. But if you went from here to here, that's your bond angle of 90 degrees. But if you went across the middle part, this would be 120 when you're going between these 3 in the middle. So that's why we have the two different bond angles here. All right, for our molecular geometry, for this one we had 4 and 1, so that's going to be a seesaw shape. And my seesaw shape down here, I should have a lone pair on the top, and then the two bonds going down, so it's going to be this one right here. So that would get copy and pasted. And now for the symmetry, the bond on either side here, left and right, if you're looking from this perspective, is going to cancel. But then when you're going around this part right here, the lone pair is not going to cancel out with those two bonds. So this is going to be a polar molecule. All right, in our next example, we have CO3 with a -2 charge. Now, I did show you an example of something like this in class. This -2 means that you have 2 extra electrons that you can kind of place wherever they are needed in order to make this thing follow the octet rule. Notice there's no star here. So I'm going to start with my carbon. I'll use X's just to make things a little bit easier for this one. I have an oxygen on the top. It's going to link once. I'll put an oxygen on the bottom. It's also going to link once. And an oxygen on the side. All right, now the only way to make this work is to take 2 of these electrons, put them in the middle. So we're going to make a double bond here. And then we had this -2 charge. That means that we have 2 extra electrons to play around with. I could leave one over there and one over there so that those oxygens are both satisfied. So I'm going to redraw this to make it a little bit neater. So I put the double bond going towards the bottom here. So I'll put that there. And then I had single bonds to the other oxygens. The oxygens with the single bonds had 3 lone pairs. And then the oxygen with the double bond had 1 lone pair. And then this whole thing would have a -2 charge. Now technically this is actually a resonance structure, so you could draw this with the other 2 possibilities for where the double bond could go, but it's not going to really impact what we're doing here, so we can just ignore that part. For our total number of bonding directions, we have 3. Remember, a double bond counts as a single bonding direction. There are no lone pairs on the central atom, so that's within the family of 3. All right, if I go across that row, this is a trigonal planar. And because it is 3 and 0, it is also trigonal planar for the molecular geometry. Bond angle of 120 degrees. And then for our picture, it's going to be this one again. This is 3 and 0. So that would get copy and pasted up here. And now for the polarity of the molecule. This one is a little tricky. It does look kind of like it would be polar because this double bond is not the same as the single bonds. Like I said before, with our resonance structures, really this double bond is actually split between all 3 of these possibilities. So really it should be nonpolar, but because this is kind of a weird exception, if you put in polar, I would also accept that for this one, just based on the way that it looks. Now, when you have your VSEPR quiz, I definitely would not give you one that's tricky like this. They'll all be relatively straightforward. All right, so that concludes part 1. So if you're just working on the section for Monday, you should pause the video now and you can continue this tomorrow. But if you're ready to go through part 2, this is what you will be completing on Tuesday, then I will continue from here. All right, in our first example for day 2, we have oxygen and 2 fluorines. My oxygen atom is going to have 6 valence electrons around it. I have a fluorine that I'm going to attach to either of these sides. So I end up with 2 bonding directions and 2 lone pairs for a total of 4 electron groups. So if I go into the family of 4, that means that this is going to be a tetrahedral for the electron geometry. The molecular geometry is going to be bent. Bond angle of approximately 109.5 degrees. Again, because of the lone pairs that are present here, it's actually going to be a little bit less than the 109.5 degrees, but that's fine for an approximation for our data table. For our shape, we are going to have this one right here. This is also a bent shape, but it only has the 1 lone pair, so we want the one with 2 lone pairs. That's going to go up there. Now, for the polarity for this one. It's a little tricky if you're looking at this picture right here, the way that I drew, and I drew it this way on purpose. If you cut it in half this way or this way, it does look symmetrical. That's why it's important to look at these 3D structures. If you look at this one, if you cut through any of the bonds, that lone pair is not going to cancel out with the bond over here. So this is actually asymmetrical. So this is going to be a polar molecule. Another way you could draw this Lewis dot diagram would be something like this. I've drawn it this way for water before, so you can see the bent shape a little bit better. But if you happen to draw your Lewis dot diagram like that, just make sure that you are looking down here when you're trying to figure out the polarity of the molecule. All right, for our next molecule, here we have a chlorine. This is Cl, not Ci, and we have 3 fluorines attached to it. Notice that it is an exception to the octet rule. Our chlorine is going to have 7 valence electrons around it, and I have 3 fluorines that are trying to attach. I'll put 1 fluorine on this side, and then I have 2 more fluorines. I'm actually going to put both on the top here. I know that typically we do space them out, but that will allow me to keep my lone pairs together, since I'm going to need them together in the end anyway. And you can see that there are then going to be 2 lone pairs here. So I have 3 bonding directions and then 2 lone pairs. It's going to leave me with a total of 5 electron groups. So I'm going into my family of 5. This one is going to be a Trigonal Bi-Pyramidal. And the molecular geometry, because I'm looking at 3 and 2, this is going to be a T-shape. The bond angle for this one is going to be that 120 and 90 combination, like we saw in one of the examples on day 1. If you did not watch that part, here this is the general shape for that family. Going from here to here, that would be your bond angle of 90 degrees, whereas if you're going across the bonds in the middle, that would be your 120. So that's why we have the 2 different bond angles here. All right, for our 3D sketch for this one, we have 2 lone pairs and the 1 bond, and it should be the T-shape. So that's this one right here. So this we get copy and pasted into your box. Actually, hold on 1 second. I picked the wrong T-shape. It should be this one. So we only had the 2 lone pairs. So that's the one that should go up here. And then for determining the polarity of the molecule, the fluorine here would cancel with the fluorine there, but this fluorine would not cancel out with the 2 lone pairs. This is going to be a polar molecule again. For this one, we have Xenon Difluoride. We have a xenon, which is going to have 4 lone pairs around it already because it's a noble gas. It normally doesn't like to bond. This is going to be an exception to the octet rule, so the xenon is going to have too many electrons around it in the end. Now you could spread out these fluorines, but I know that I would just have to redraw it in the end anyway, so I'm going to put both of these fluorines up here. That way I can have all of my lone pairs together in the end. So I'm going to have 3 lone pairs and then the 2 bonding directions. So 2 bonding directions, 3 lone pairs, that is a total of 5. All right, so for this one, I am within the family of 5. So I'm going to look across, and this one is going to be Trigonal Bi-Pyramidal again. For the molecular geometry, because it's 2 and then 3, this is going to be a linear shape. And the bond angle is going to be 120 and 90. All right, now for picking out my picture, I should have a straight line with lone pairs that are all around it. And actually, it might not be, oh, nope, there it is. It's right here. I thought it might have gotten cut off onto another page. So this is what we're going to copy and paste into our 3D sketch. And now for the polarity. These 3 lone pairs are actually all within the same plane. If you looked at it as this picture, these would be the 3 lone pairs, and all of them are going to cancel out. And then we have the fluorines on either side that are going to cancel out. So this one is going to be a nonpolar molecule. Definitely cannot tell that from this. So again, it's really important that you're looking at the structures down below. All right, in this example, we have NH4 with a +1 charge. This +1 means that we're going to have 1 extra electron that will then be taken away. Now, just to make things a little bit easier, normally I would draw in all 5 of nitrogen's valence electrons. But since I know the 5th one is going to be taken away because of that +1 charge, I'm just not going to write it in from the start. So I've taken away that 1 electron, it's been given to some other ion, and then I'm going to connect my 4 hydrogens on each of these sides. Alright, so this is going to be my structure. I have 4 bonding directions, 0 lone pairs, so a total of 4 electron groups. It's going to be part of the tetrahedral family. There's also a tetrahedral molecular geometry because it's 4 and 0. Bond angle is going to be 109.5 degrees, and this one actually is exactly 109.5 degrees because there are no lone pairs around our central atom. For our 3D sketch, we want the tetrahedral, which would be right here. And then for the polarity. Nitrogen to hydrogen is a polar bond, but all 4 of these are going to cancel out, as you can see from here as well. So this is going to be a non-polar molecule. All right, next we have SF6. It's going to be a sulfur in the middle with 6 valence electrons around it. We're going to have a fluorine on 1, 2, 3, 4, 5, 6, 7. So a fluorine attaching here and here. Put one over here. I still have 3 more. So in this example, we're actually going to have a fluorine attached to each of these valence electrons that are hanging onto the sulfur. So we're going to have 6 bonding directions, 0 lone pairs, so that is the family of 6. Our electron geometry is going to be octahedral. Molecular geometry is also going to be octahedral. Bond angle is going to be 90 degrees. And for a 3D sketch, we are looking for this one right here. So we have all 6 of our bonds. And because all 6 of these bonds are polar and they're all exactly the same combination, sulfur to fluorine, they're all pulling in equal and opposing directions. This is going to be a non-polar molecule overall. Alright, so that completes our tutorial for the VSEPR practice on Google Classroom. If you still have any other questions, please reach out to me through our weekly mailbag and I'll be happy to help you.